Pleasure to be here. I mean, again in Trento, and to discuss also. I mean, I am nuclear physics, basically a scientist, and it's always nice to share ideas and work with other communities. So, what I will talk about today is the link between neutron system essentially and atomic system, and a work we started a few years ago. And basically, the question was, can we use what people are doing in other fields to help us understanding our systems? So we are working with self-bound system with a very strong interaction, and it is known as a hard problem. And one thing we wanted to look is, can we develop density functional theory in a different way for atomic nuclei? So I will talk about all these topics, and we look at many things actually, which and we had quite interesting results. I would like to say that I mean most of the work were done by students. One is here, Antoine. So come, it's a pleasure now. He's postdoc in Warsaw, so it's a pleasure to have him here, and other people with me working in Orsay. So should I switch like this? Yeah. So just to make a short summary of what we are doing in nuclei, or in many body physics for atomic nuclei. So I told you it's a hard problem. So we start with, so yeah, I give you the ab initio side. So we start from an interaction that we can improve gradually. So we have a power counting and things like this. And we do a complex calculation. I think it's what we call ab initio. So we try to solve exactly the problem within a certain precision. And then we end up with spectra, which could be nuclear, I mean, binding energy, as a function of mass, or reaction things. So it's very hard. And this is where we are on this side. We are able to touch part of the nuclear shaft, but a tiny part, because it's a too hard problem. I'm not from this side, so I can say it's very nice. I'm from the other side. So and I take the problem much simpler. So we have a cell-bound quantum droplet made of fermions. And it turned out that there are many things that we can really easily grasp using density functional theory. So which means that we reply the problem by a very simple problem based on one body density, and we can treat many things. So essentially we do a very sharp approximation. So we have an interacting problem with two bodies, three body interaction, and so on and so forth. And we map it to a independent particle problem. So as many people do in physics. And then from that, we can do, it's quite amazing. I mean, the predicting power is quite amazing. We can do density of nuclei. So the points are, different nuclei. The points are experiment and the line are the theory. We can do thermodynamics and apply it to neutron stars, for instance, and it works quite well. And we can do also, and this is something I'm developing, so we can do time-dependent evolution of cell-bound system leading to fusion, fission, or whatever. So it's quite versatile, and we can do many things. But there is one thing that is not so clear, is why when we do a density functional theory that is very simple, it works so well. So it's a basic question. I mean, we have a hard problem with a strong repulsion in the interaction. It's highly non-perturbative at the first place. And at the end, when you look at the energy of the system when we do a DFT, it's kind of trivial. So I put it like this. So it's a kinetic term plus a density dependent term. And well, I mean, with 3 or 4 terms, you made the job in first approximation. And this is where the unitary gas is coming. I mean, you cannot imagine a simple density function that unitary limit, because the energy becomes a constant time the Fermi gas energy. So could it help? So this is what we started to look at. So we came back to very basic things. So it was nice that you talk about the Lee Young formula and beyond mean field. So we actually did the same. I mean, what are the limits we know of a system when we want to expand the system in terms of density or Fermi momentum? So we look. So we took the theta of Valeshka, where you can find many things. So we look at this, and the most simple thing you can do is to make perturbation theory. So you go from R3 Fock, second order, you get the Lee Young term, called beyond mean field correction. And this is where we are. So this is the simplest we can do. So we have kind of idea that our energy could be written in terms of many body perturbation theory on one side, or in terms of coupling constant, I mean strength of the coupling constant on the other side. So here I put the S-wave scattering length and the effective range. And what we want to do is to start from the low density weakly interacting system to go to the high density strongly interacting system. So I put here the number we have for the scattering length in neutron system. So it's this in our units in Fermi and this. The problem is that, I mean, the validity where this times the Fermi momentum is less than 1, it's very narrow. So it's 10 to the minus 6 Fermi to the minus 3. So essentially, when we look at the equation of state of a system, so here I put the symmetric matter where you have the same number of protons and neutrons. So it's stable, you have an equilibrium. And there is a neutron matter where you have only neutrons. So what is the region of density I'm interested in? It is here, around 0.16. I mean, the equilibrium density. So the problem is that in our system, the perturbative regime is here. So we are at the density which is several order of magnitude lower than where we are interested in. So this is where we are interested in. And here we have this value. So I put it basically for the neutron matter. So we have this that is equal to 25. So you imagine that no perturbative expansion will work, essentially. But also this, the effective range is important. So, and this is where atomic physics or atomic system are less interesting because you have a real, I mean, the value of this could be neglected in most of the experiments people are doing. And actually the P waves start to be also important. So we cannot fully neglect it. So this is the basic. So you cannot use perturbative regime. We cannot stick at the low density limit. So essentially Lyon should be used less. But actually there were some work. So we cannot use perturbative expansion, but we can use resummation of diagrams. So imagine that you select a class of diagrams. If you are able to sum up all the diagrams to infinity, eventually you can treat non-perturbative effects. So this is well known. So this is one example where people are doing resummation of particle diagrams. And okay, if you do this, what you realize is that the energy you get will be, so it is typical Taylor expansion to get the perturbative expansion. So it's known, all these things, it's nothing special. But you get a ratio where the Fermi moment, the A comes in the two parts. So, and this is why eventually you can get a final value at large energy. So this is a very complicated phase space for the two particle collisions. So, but this is still not so useful for us. So, but what is interesting is that when you do this in practice, you get something that is not so wrong. So here, I suppose this is a reference curve. And here it is the type of curve you obtain with this formula, depending on which diagram you retain. So you see that you can, I mean, the nice part is that you have any order in the expansion, but the problem is that the result strongly depend on which type of diagram you have. So eventually you will never be able to do anything with this. So we were quite new in this field. So we are thinking, okay, but this is complicated for us to do this phase space integral. So we are not so using the numerics to do it, but there are very simple arguments. I mean, imagine that instead of doing this, you just keep the functional form, and you assume that if you develop this, you get the Lyon formula. So this is not by us, actually, people try to do this. So at least you know that the two first order are correct. So a second possibility is that you assume that instead of doing for real the integral, you just take the mean value. And then you have just a factor that come like this. This was discussed in this paper. I think that was never published because it's too easy. But yeah. So, but the point is that if you take this and you take the limit of infinite scattering length, I mean, you get something that is not so bad. I mean, 0.32. If you take this one, it's 0.4. So eventually, you are not so far from the Birch parameter. So this was what puzzled us, actually. We are thinking, okay, maybe it's not the correct way to do, but at least you will get two limits that are correct: the low density limit, perturbative limit, and the high strongly coupling case, unitary gas. So we did even a more pragmatic approach. Okay, we say, but why don't we take the unitary gas as a limit, as a specific limit? So we want to target exactly the unitary gas. So which means that we took this type of form, and then we have only two parameters. So it's really by hand functional theory. And you impose the two limits, so low density limit and unitary gas limit, and you fix this value to the best experimental value. And oh, you see, it's not so complicated. It's much simpler than doing the phase space integral. And actually, it's not so bad. Just to do that, I mean, you have a DFT. So here I show, I mean, the experiment in cold atom system. So you have energy as a function of energy of Fermi gas, and here you have the ASKF. So here is the unitary gas limit. So there are different things I will not talk about, but essentially you have different experiment or different theoretical experiment where you do the quantum Monte Carlo case. And here is the blue area is when I take a Bohr parameter between 0.37 and 0.44, which was at that time more or less the uncertainty on this. And you see that what you have is that, of course, you are correct here, but also the shape is quite correct. So I fixed a point here, and I fixed a point here. This is all what I did, actually. And the rest seems to be OK. So from my point of view, it means that essentially the form of the functional we took is not so bad. So this was the starting point of the story. So we can do, I mean, once you have the DFT, everything becomes simple as soon as your observable depend on the derivative of the density or the density itself. So we look at the tan parameter, the contact tan parameter, and well, since this is good, this is also good, and it works. And you can systematically address most of the, I mean, not all, but some of the observables that are defined as the derivative of density. It's a pressure as a function of the scattering length times the Fermi momentum, the chemical potential, the compressibility, and soon velocity. Here you have all the experimental observation. So so it's quite yeah, sure.
You show on a side of the resonance.
Yeah.
Because if you do for a little bit different system, you can have the Fock theory, which is a way to you recover your equation.
Right, probably. I mean, this is one point. I will come to this a bit about
On one side, you have the downstate.
Yeah.
Can it be that if you proceed on the other side of the resonance, it's less accurate?
Well, of course, you have, I mean, if you look at the formula, if you take a positive scattering length, it will have a divergence. So it will work a little bit in the other side, but at some point you collapse. So, and this is not.
Because of the bound, because I can tell you that looking at the Fock is precisely the point. That if you include another bound state, you are able to have a single line for both.
Well, yeah. But I think you are going too far in the interpretation, because honestly, it's just a formula, and where you have you cross zero in the denominator. But I understand your point. I mean,
the same expression with another
yeah, but then no, I agree with you. But if we want to do this, I mean, the way we solve the problem will not work, because then we have a bind state, and then we have to do a different equation. I mean, a different DFT. So if you have a bound state, you have to account this degree of freedom in addition, which is not the case here. So yeah. So where we are, I mean, with this. So I started from general things in perturbative expansion, resuming diagrams. So is it predictive? So I just put it seems so. Okay, so because it seems to reproduce many things. It doesn't mean that we have the right physics, but it reproduces something. Is it really useful? Well, not yet. Not yet, because of the problem I mentioned before. I mean, scattering length is very large, so this is okay eventually. It's not exactly, this one is not exactly infinite, so we are not exactly at the unitary limit. But more than this, we have other component to account for. The effective range in particular is very important. It's far from being small, and you see it's far from being less than 1, so it should be also resum in some way. So it could not be just used like this, because we can do like Lee-Yang perturbation theory for the effective range. You will get a formula, but then it will not work because we are above 1, much above 1, and the p wave should be accounted for. So we started to think about this, and also there is something. I mean, we even put in no information about effective mass, superfluidity, and things like this. Why we know this has a superfluid system. So it's really a DFT just on the density, not on the anomalous density. So, well, to solve the first thing is we should introduce the effective range. So what we did to do that, I mean, actually, we started from the mean field artifact theory. You can write the mean field theory for the including the effective range, and it will give you a Rossum formula. So we just kept the functional form from the mean field theory, and it gives you this type of shape, okay? And you just have more factors to adjust. And this is why the quantum Monte Carlo were very useful, because okay, we know the expansion in the low density limit, but then we were needing the expansion in the effective range. And so there were people, especially from nuclear physics, that use the same technology as for cold atom, and they look at how the Birch-like parameter was evolving with the effective range. So we use this. So we have few parameters. Here we have few parameters. You adjust. So there is a single, I mean, there is a one-to-one correspondence between them. But then you have to see whether this, I mean, fitting this on this can reproduce something. So what we did actually, we have now density functional theory that depend on the, I mean, the scattering length and the effective range with some correction, with some non-perturbative correction, let's say. And we just look at the result of the DFT compared to quantum Monte Carlo problem. So here the points are all coming from the quantum Monte Carlo of Alex and Joe Carlson. And they did cold atom and neutron matter with the same theory. I mean, with the same. So the difference between the points here and the point in neutron matter in green is that here you don't. I mean, you have infinite scattering length, while here you have finite scattering length and effective range. So with the same functional theory, we obtain these two lines. Okay, and it seems to work to some extent. So without adjusting anything, we were able to reproduce the quantum Monte Carlo results just based on simple asymptotic arguments, which is very nice because it's not the way we do normally in nuclear physics. We adjust some data. Yeah, this is just to show you here the Lee formula, so where it works. Still, I mean, when you write it like this, I mean, this point here is like here, it's 0.01, so we are still far away. So here is the energy as a function of density, as we have used to show. Here it's in Fermi, sorry. And this is the ab initio method, I mean, and this is what we obtain for these two curves. So it's very nice because we are in between the two, actually. I mean, here it's cold atom, here it's neutron matter based on this. But here we expect to have a P wave, D wave, and so on. So we have all the waves. I mean, so we are still, I mean, we kind of progress because we have something where we didn't tune anything except on the ab initio calculation, where it's not so bad, actually. So it's already a step. Yeah. So we try to apply this to neutron matter, and one thing that was puzzling to us is the static response of neutron matter. I mean, this was also a calculation made by Alex on the static response as a function of the transfer momentum. And this was the situation, actually. Here is ab initio or exact calculation in red crosses. This is a free gas in black case, so you have absolutely imagine that you don't have any interaction. And this is what I call empirical density functional theories, and the one we use in nuclear physics when we adjust to data. So you see that when you use the best interaction, I mean, the DFT you have on the market, you are completely off. And it seems that the free gas is compatible with the case of strongly interacting gas, which is, for us, was very puzzling. So we try to see whether our functional can do better than this. And we started with, so we didn't add this for cold atom. So we took also a result taken from the superfield local density approximation of Forbes and Sharma. So this is a point. And we just did the same with our functional. And actually, we are quite good. We are quite sensitive also to the value of the Birch parameter. So we started with 0.37, the blue curve, and realized that in the calculation of Forbes et al., they were using a Birch parameter that is slightly higher, 0.4. So we took the same and actually we reproduce this. So it seems that at least for the cold atom, we are in the right direction. And then we look at neutron matter where we plug in the effective range. So this is what we obtain for the static response. So, and compared to our functional. So we are not completely in the curve. The density is already quite high. And then we just put the leading order of the P wave, which give you the curve in green. and this is what we obtain. So actually we are quite, I mean, the shape is correct, and we are in the right direction. So we are progressing. I mean, beside the fact that we reproduce something, which could be called atom or nuclear matter, I mean, my first question was, do we gain something in looking at the unitary gas as a limit, or making expansion beyond the unitary gas? I mean, still, I mean, this functional is far from the simple one I've shown here. And I want to understand why this simple one is working. So what we did actually is that we interpreted this as a density-dependent coefficient, or KF-dependent coefficient, so like in a Lee Yang formula, except that now you have renormalization of the coupling constant. So if you do that, I mean, the idea was you start from this and you try to write it like this, and you just look at what is happening. So it gives you S-wave coefficient and effective range coefficient like this that depend on density, and then you just write it and plot it. And this is what's happening, and this was maybe, for me, it was the main result, actually. Yeah? Not the functional itself that could be used, it's very easy, but the point is that if you look at what's happening when you plot the effective scattering length as a function of density, here you start from the physical value. It is strongly and rapidly renormalized to some kind of plateau at the density where you are interested in. So if you make a zoom of the density where you are interested, actually it's almost constant. And what was obtained for free is actually, if you look at the constant you have, I mean, this is this area in green, you plot it for different, I mean, it is this area. Here it is a zoology of the DFT we use in nuclear physics. And the value of this coefficient in this functional, I mean, it is one of these two, this one. Actually, you realize that the error, I mean, all these functional are within the error bar of our renormalized scattering lengths. And it's worse than this. I mean, you can have analytical formula for this functional as a function of the Birch parameter. So eventually we can forget about this functional and just take this value. And it's not fixed anymore by n, not fixed on observation of nuclei. It's fixed by the Birch parameter. So we gain something in the sense that we understand why. Because of the fact that it is constant, you can take this as a constant in practice. So at least we understand one of the terms in your functional. So I think we gain in understanding why we have a very simple functional in nuclear physics. Yeah. So I mean, in practice, I mean, it's not enough to understand one term. So what we did is that since we were knowing this type of DFT with the shape of the DFT, we proposed several DFT. So based on different arguments. So one of the DFT we proposed was the extended Lee Yang Orsay, where we basically took a density-dependent coefficient, which looked very much like the one we have proposed. I will not enter into the detail of this, but it's just to say that we are proposing different type of functions. Another one is using the renormalized formula for the density, where we are able to reproduce at the same time the low density limit and the saturation, I mean the equilibrium limit. So this is the type of things we do, and now we are able to apply to nuclei. So one of the things that we did after this first work, I mean, there were several problems. So we have just the energy, but we know that when we look at the physical system, we want to have more information like effective mass, pairing gap, or something like this. So we try to see if we can work in the same way at the level of self-energy. So where you have everything encoded. It was much harder. Actually, it was the PhD of Antoine. So, I mean, the strategy was simple. You select a class of diagram, you perform resummation, eventually you use the phase space argument, where phase space meaning that you get rid of the integrals, and then you check that the result is predictive. So we did it, and the first question was, can we do the same for the self-energy? And what we did, I mean, we cannot do whatever you want in this game, and because very fast you have problem with mathematics. So you have to become expert in Mathematica, essentially. So, or you will be hired by Mathematica at the end. So anyway, so Antoine took the later approximation, and well, I mean, you have to break. So if you work at the level of energy, you have this type of closed diagrams. When you work at the level of self-energy, you break a leg of the diagram, and then you get after some some lengthy calculation, you get this. So this was worked out by Kaiser with some formula. So it's quite messy, but okay. I mean, you can go to the end if you select the proper diagram. So what we did, I mean, okay, we start from this, and then we get here is essentially, so this is the energy, which is an integral of the self energy. So for the energy, the phase space was just to replace this by something like this. Can we do the same for the self energy? Well, it was a bit complicated. So we started to think about it, okay, what type of expression we can have on the self energy. So we took again the Fetter and Valeshka or any textbook. Okay, you know that if you start from the energy, the way to introduce self energy is so you do particle excitation, and then you get the self energy with a real and imaginary part that is connected to a single particle energy and lifetime of the quasi particle. And eventually you have all the possible connection to effective mass and things like this. So this could be also done. The same guy did it. So it took a while to Antoine, but we also got the same expression. There are several difficulties here. I show the quasi-particle energy as a function of its momentum with respect to Fermi momentum. So this is what we expect to have in Bruckner R34 or in some reference, and this is what you have when you do the integral. So it's so the difficulty is that it has very bad predictivity. So the starting point is very bad. So essentially, this integral is not working at all. So meaning that we have not selected the right diagram or whatever. I mean, so it was not so. So the conclusion is that it was not evident to make a phase space equivalent to this. So we did something different. So we started from the energy and we tried to map this at the self energy. So the energy, you write it like this, but this term is just the function of some function at k equal kf. So you go to the chemical potential like this. So you can directly obtain this from this by taking this property. And then you say, okay, now I want the energy. So this one is the energy, the chemical potential is the quasi-particle energy at k equal kf. So let's just take this value and you replace kf by k. And this has the advantage that you get the right Galitzky formula at low density. So it was just a trick to go step by step and to have a functional form for the self energy. And this was a bit strange that, you know, sometimes simple approximation work quite well. So actually, this is what you obtain. You do this without adjusting anything. This is a quasi-particle energy as a function of kf. So I told you the blue curve was not working. It was performing the integral. The green curve is the Bruckner R34, that is what we have as a reference. And this is what we obtain here with this trick. So it seems to be quite interesting that it works. See, also, I mean, it was just a trick. And we look at one of the things we wanted to look is effective mass as a function of SKF, and here it's some reference curve. And here we show how it depends on the type of diagram we took. So it's very empirical, but I will come to my conclusion actually. Yeah? So you see where we are. I mean, we take complicated theory and we try to find a simple approximation of the complicated theory that is predictive, trying to not adjust everything. I mean, on data, trying to adjust on some reference. So, well, I mean, the conclusion at the stage we are is that it works to some extent. So, and it was actually nice to see that we can connect, I mean, our coefficient to the Birch parameter, also in neutron matter. Well, we can apply them. It could be successful in some area of physics, in atomic physics or nuclear physics, still in quite low density. Well, the way we use it, actually, we use it as a starting point to develop new type of functional, modern type of functional, which are mixed between empirical and ab initio-based functional. Well, the problem is harder on the self energy. So, well, at that stage, this is why I decided to stop working on this because it was too messy in terms of mathematics. And at the beginning, I say, okay, without superfluidity and problem of selection of diagrams. And I discussed with Antoine actually recently, well, yesterday. And he told me that, okay, they solved the problem of superfluidity. So now I was happy to see that Antoine has developed his own research and incorporated superfluidity in the game of mapping a very complex system into a functional theory. So he did it with a group of Warsaw. And voila, it's nice to see that things is evolving. Okay, thank you.
Thank you very much, Denis. Questions from the audience? Yes.
So my name is Piotr Magierski, and I have a question concerning this comparison with the unitary regime. So part of this energy comes from the anomalous density.
Yeah.
So
but this was the problem, actually. We were able to get a functional theory without the anomalous density. So which make almost the the dead of the without being superfluid, while you know that the system is superfluid, is problematic. It means that exactly normally the energy should be split into two pieces. One should be the pairing energy, and we don't have it. So in some way it should be it is mimicked in some way. But of course, if you look at the response of a superfluid system, you will have a gap that we will never have here. This is why we were very much interested in looking how to extend the superfluid LDA, where you took the effective mass gap and the rest consistently. But we started from a non-superfluid gas, actually. So, well, the thing is that there is some inconsistency in fitting the burst parameter that is really on a superfluid system using the functional. We should have fitted the non-superfluid case, which is 0.4. We can do it, but at the end it worked quite well like this. Of course, if you want to do dynamics, it will fail. So this is where we are. Also, it starts to be very complicated. So, the fact that you arrived with Antoine to generalize it with superfluidity is a starting point of the story. Yeah.
Thank you very much. So is there any question? Yes, there are a couple of questions. So let's start with Srimoji. I don't know.
Hi, this is Sri. Can you hear me?
Yeah.
Yeah, I have a question. Can you include a finite temperature in your analysis, and how would one go about doing that?
Well, probably yes. We didn't make it. Normally, it's a DFT that is just function of the density itself. So the density, if you have occupation number of the single particle state, we do it usually with our DFT. So it's a self-consistent process to adjust the temperature by fixing the occupation number with a given Fermi shape. Thomas Fermi. So this we can do. We have not made it. Of course, if you are superfluid, it will. We have to work on the quasi-particle levels. But a priori, once you have the energy as a function of density, the density itself could be parameterized in terms of occupation number of single particle state. So yes, we can.
Okay. All right. Thanks.
The next question is from Thomas Papenbroek. Please unmute yourself.
Hello, Dennis. Nice talk. I wondered if you, for instance, you seem to get energetics of superfluidity without a superfluid. And I wonder, for instance, if you would crank the system, would the moment of inertia be those of a rigid liquid body, or would it be of a superfluid?
Well, it's a good question, but honestly, I don't know. If I crank it, you will have. If you crank it too much, you will have pair breaking effect. This we know, but in this case, with this simple functional, I'm not so sure when it will happen. Yeah.
Thank you.
Yes, please, Alex.
Okay, so I have first a comment, right? So Li, Yang, or Sei sounds a little bit like the analytic continental divide in philosophy. Like one part is geographical and the other isn't. right? Or say is a place, and Li Yang are names, right? Anyway, but that's a kind of a silly aside, right? I have a question about the density dependence of the static response function for the P wave case. Could you maybe go back?
Yeah.
So you had predictions for 0.1 and 0.04, and then on the right, bottom right, I mean, you can't really tell, but it looks like maybe the 0.1 is doing even better, no? Or maybe I'm misreading it. No, yeah.
Yeah, but it's but I don't know how far we can go in trusting this because once the P wave is starting to act, normally we should have also higher order component. Huh?
Yes. So this could be a fortuitous cancellation of higher order terms.
Yeah, but this is a question actually. This is where we were. I mean, the good part is that we were having the good shape of the static response, which was not the case for the traditional what we call Skirm functional theory. But then, I mean, the test on the P wave were just like, okay, we put the P wave, the linear contribution, and then we just look what's happening. So probably, I mean, it's just a test. I mean, we cannot say much more on this. At density 0.1, you are more than P wave. This you should probably see in your calculation.
But like you responded to Thomas's question, right? So, you don't have superfluid degrees of freedom, but you capture superfluidity. So similarly here, you call it S wave, you call it P wave, but, maybe effectively they're capturing more than that, right?
Yeah, right. And as soon as I fit on the superfluid system, I have more than this. That's clear.
Excellent. Thank you.
I mean, at some point we stopped to really use the functional because we were not able to put the superfluidity. And this was, I mean, we know we have to. We have to. So to progress, we have to have superfluidity. Or we work at high temperature, which is okay. But
okay, so let's think this again.